When a standard Windows forensic tool encounters an unrecognized target drive, the GUI might freeze or fail to mount the volume. At that point, the investigation shifts away from commercial software and moves directly to the kernel level. Unix-like systems, such as Linux distributions and Apple's macOS, run on architectures entirely distinct from Windows NTFS. In these environments, raw data is completely decoupled from the file names and directory paths users see on their screens. This separation is managed by specific structural elements, Inodes in Linux ext4 and B-trees in Apple's APFS. To recover evidence, carve deleted data, or navigate a corrupted drive, an investigator has to dismantle these specific architectures layer by layer. Mastering native Linux command line utilities provides a forensically sound method to bypass operating system restrictions and extract block-level data from resistant systems. The primary rule of Linux architecture is absolute uniformity. Every single system element, up to and including hardware interfaces like dev.sda, is treated strictly as a file. Before a single piece of user data is written, the Linux file system organizes the drive into a strict four-component partition. The first is the boot block. Residing solely on the main hard disk, this block contains the critical bootstrap code required for system startup. Next is the superblock. This component governs the drive, specifying the disk geometry, tracking available physical space, and managing the configuration of the entire file system. The third component is the inode block, which holds the very first data positioned directly after the superblock. Finally, there is the data block. This is where the actual binary content of directories and files is physically stored. This rigid four-part hierarchy guarantees operating system stability. But for forensic investigators, it means reconstructing raw file content requires tracing precise, scattered metadata paths across the disk. In Linux, that metadata is housed in the inode, or index node. This data structure serves as the exclusive container for file details, logging the user ID, group ID, modification times, and link counts. However, inodes do not record the actual file name or its directory path. Instead, the operating system relies on a tiered pointer system. As a file grows, the OS creates layered addresses that link outward to highly dispersed data blocks. Here, the primary inode configuration links via direct pointers to the first 10 blocks of data. When exceeded, the system generates indirect pointers, linking to 128 new addresses. For massive files, the architecture utilizes double and triple indirect block addresses to manage the fragmented data. This pointer system characterized earlier Linux distributions, but the modern ext4 standard actively mitigates this complexity. ext4 introduces extents, contiguous areas of physical storage. By allocating space in these larger continuous blocks, ext4 drastically reduces file fragmentation and largely eliminates the need for indirect pointers entirely. When facing a severely damaged or intentionally formatted Linux drive, an investigator must manually parse these remaining pointer chains and extents to extract the surviving data. Apple's storage architecture approaches data allocation differently, evolving from the legacy hierarchical file system to the modern 64-bit Apple file system, or APFS. The baseline unit of Apple's storage hierarchy is the logical block, which holds up to 512 bytes of data. As shown in this breakdown, these baseline logical blocks are rarely utilized individually. Instead, the operating system merges multiple consecutive logical blocks, in this case, blocks 0 through 3, to form a single, larger unit known as an allocated block. To further minimize fragmentation, macOS groups contiguous allocation blocks together into larger structures called clumps. When a macOS file increases in size, it populates its assigned clump sequentially. The OS will only allocate a new clump once the current one is entirely full. File endings within these blocks are strictly tracked. The logical EOF marks the exact byte where the actual user file data stops. The physical EOF marks the total bytes allotted for that file, leaving a large gap of empty space. This remaining gap is called slack space. Examining the gap between the logical and physical EOF frequently yields fragments of deleted files or critical hidden artifacts. With the shift to APFS, Apple entirely abandoned the use of inodes. Relationships between files and directories are now maintained using B-tree data structures. In a B-tree hierarchy, the actual user files function as leaf nodes, systematically organized and retrieved through header, index, and map nodes. APFS also integrates point-in-time system snapshots. While these snapshots disrupt traditional linear timeline analysis, they provide significant yields for bulk data recovery. Extracting this data requires navigating Apple's hardware-level encryption. Systems utilizing FileVault 2 present an immediate barrier, requiring the investigator to extract specific master or recovery keys from RAM or the user. Physical extraction is equally restricted. The Apple T2 security chip and the native secure enclave often prevent investigators from removing the drive to perform a standard imaging process. Even connecting external devices carries risk. A macOS feature called disk arbitration automatically mounts connected USB or FireWire drives, which can alter exact evidence timestamps if not explicitly disabled. Apple's combination of layered structural abstractions and a hardware-locked ecosystem actively resists standard data extraction. Investigators must deploy specialized low-level bypass methods to secure the evidence. To bypass OS-level restrictions and safely interface with raw block-level data, investigators utilize Kali Linux. As seen in the Kali interface, the distribution includes an expansive suite of native forensics tools right out of the box, offering immediate access to carving utilities, forensic imaging tools, and the SleuthKit suite. For disk acquisition, the DC3DD command line utility serves as a forensic-specific upgrade over legacy DD or DCFLDD commands. This output demonstrates the exact syntax for block-by-block data acquisition using the if equals dev/sdb2 structure. During execution, DC3DD provides real-time progress reporting, tracking sectors copied. Crucially, it performs on-the-fly verification, generating matching MD5 hashes for input and output to prove the copy is identical. An investigator's success depends entirely on their tools. Mastering the intersection of raw file system architecture and native Linux command line utilities ensures forensic integrity, securing the data long after a standard GUI has crashed.